welcome to the day 8th class of certification program on machine learning and GenAI. So from the feedback of yesterday, I have seen most of the people are not able to understand my voice yesterday. So the voice is something like some breaks are there in my voice, and you can't able to hear that audio. Today we thought we have worked a little bit, and we uh, we solved that problem. So if you have still persisting, the same problem is persisting, please uh, give the message in chat box. So I'll just want to recover whatever we have learned yesterday, because most of the people are completely out of focus from the yesterday's class due to the audible problem. So yesterday we have discussed about all the basic concepts of how many activation functions are there, what activation functions, what is the activation function, and how we can use that activation functions, what is the use of the activation functions. And then we have come across through loss function, different types of loss functions, and how we can use a loss function, and what type of loss functions in particular cases where we'll use that we have discussed. And then we'll move on to regularization problems. So we have learned what is a regularization, and what type of regularization elements are there, and when you have to use a particular regularization uh, type for a particular algorithm. That and all we have seen yesterday. And of course, we have seen a simple hands-on problem on how to build a neural network, a simple neural network, how to build that neural network, and we had seen that how to operate that, how to deploy that neural network, and how to build a layer by layer structure. So that and all we have seen yesterday's class. And today's class is completely focused on convolutional neural networks, and of course RNN neural networks. So before going to convolutional neural networks, I'll just want to brief something. Yesterday we have seen the basic neural networks. So we can call it as a artificial neural networks. So in artificial neural networks, yesterday I told you we have minimum three layers. So three main layers are there. So one is a basic of input layer, and one is a basic of input layer, one is like hidden layer, and the next one is output layer. So three basic layers will have, and whatever input layer we have is only to pass the information to next layers. And hidden layer, that is like a controlling unit or processing unit, whatever you talk, that is where everything, whatever you want to operate, whatever you want to take the actions, everything happens in that hidden layer. All the mathematical actions and all the learning thing, everything happens in the hidden layer. And then finally we'll come across through the output layer, where we will get the our predicted output. Then we will compare the predicted output with our original output, and then we can able to calculate the loss, how much loss we have. And then uh, from that loss we can able to say whether our ANN is a efficient one or not. So this is the basic working of artificial neural networks. One input layer, one hidden layer, and one output layer. In between, to make it like, if nothing is used, only these three layers are used, it's just like a something flat. Any creativity, just like yesterday I have taken one example of, if you have a robot and you asked her you asked the robot to make sandwiches. So if nothing is there, only these layers are there, it's just like a flat, keeping a bread and on butter, and keeping a bread on butter, keeping a bread on butter. So it's just like a flat thing. So there won't be any creativity. So to make a little bit creativity, we are adding bias to that input layer, input nodes. Whatever input nodes are coming, we are just adding a bias. And also, every node don't have the same important when you are doing some work, practical work. Some nodes will have more weightage, and maybe some nodes will have a lesser weightage for a particular algorithm. That's why we will add some weight to each and every node at the initial state. Once that layer is working, it is passing the information to the hidden layer, and once the output layer is output we got, then depending on the loss, the weights will be updated again, and then that is processed, and the loss will be minimized. So that is there. We are adding the weights and of course bias there, and also we are adding one more function there, that is activation function. That also yesterday I have discussed. Activation function is just like it will decide which neuron should be activated a particular time. So maybe if I have a 10 neurons, I need not to activate all the neurons at a time. Maybe second and fifth neuron may be activated for a particular application. So in that cases, activation function will take the lead to tell the particular second neuron to activate at that particular time, and how much time it should be activated also decided by the activation function. So then after going all these processes, then that layer, the information will be passed to next layer like hidden layer. Then hidden layer again, all this happens, all these adding of weight, adding of bias, and adding of activation functions, all these will happen, and then it will move on to output layer. So this is the basic structure of artificial neural network. So yesterday we have seen, we have stopped that hands-on practice in the middle because of the time problem. So today first we'll complete that, then we'll move on to CNN, convolutional neural networks. Yesterday already we have shared this link. Yesterday we have shared this link already. So I'll just explain the syntax, how a simple neural network we can build. Here, so here I have considered a simple data of two features I have considered for the X. Two features I have considered for the X. Let 2, 9, 1, 3, 6. Only two features I have considered. Two features I have considered, and two features I have considered, and I have considered one variable in my output function. So just to say, the features are like a student, how many hours he's sleeping and how many hours he's studying. Maybe that two are my features, and my label is like whether he can pass the exam with these features or not. That is my label. So that's what I have considered here. The X and Y I have considered here. And next thing here, the next step I have done, X equal to X by NP dot A max. That is nothing but normalization of the elements. So in that column, everything should be in the same, consistent level. All the values should be in the consistent level. So if you want to plot these a graph between these variables and features, it will be very difficult to plot because one is in one range and one is in 80s range. So that will be difficult to plot. So we have to normalize first. So for the normalization, anything, either you can take the mean of that, or you can take a maximum number from that column, and you divide or differentiate as something you do, some operation you do using a constant. So that is nothing but normalization. So for the normalization, here I am considering NP dot A max. From each column, I will consider a maximum number, and I will divide with that number. Each number will be divided by that number from that column. So first column here, my first column is 213. So in that 213, the maximum number is 3. So I'll divide all these three numbers with 3. And the whatever values I am getting, I'll take it as a matrix. And of course for the Y, I am taking just 100 value. 100 as a constant, and I'm going to divide each and every value with 100. So that's what I'm doing as a normalization, a constant I took. And second thing is I'm introducing to the mission like some activation function I have to use. So that activation function here I am using is sigmoid. So sigmoid function, first I have to introduce to the mission. So I have to tell what is a sigmoid function. So I'm introducing that, define sigmoid. I'm going to define sigmoid.
So the sigmoid function is nothing but 1 by 1 plus x power np dot some value exponential of x, some x. Well, x is nothing but here mx plus c, the straight line slope and intercept. Whatever values I am getting, that I am going to take it as a exponential, and then I'll divide that by 1. So that is my sigmoid function. So I'm teaching that mission that this is my sigmoid function, and I am going to use this function as my activation function. And the next thing is, after taking the sigmoid function, my final aim is to minimize the loss. So everywhere, anywhere, if I want to minimize the loss, I have to derive that function and equate to 0. That's what I am telling to that mission. First, you take the derivatives of the sigmoid function, and then now I will take the initialization. So if I have a neural network, means I already told you I have 3 layers: input layer, hidden layer, and of course output layer. So in between input layer and hidden layer, I have weights and also bias and also activation function. So starting, I have to initialize each and every value, because at the starting level, mission don't know how to update all these values. So first initializing, I'm taking input layer neurons. I have considered only 2. Already 2 features I have considered, and output neurons I have considered 1. And of course hidden neurons, I'm taking some 3. I randomly I'm taking 3. And the learning rate I am updating as 0.1. At 0.1% of speed it has to learn. And epochs, some epochs means the completion of a cycle, a iteration, that I'm asking the mission to do a 7,000 times to learn the complete the relation between feature and output. Next one, here I'm just initializing the weights and biases. So weights, WH is nothing but first hidden layer weight to that hidden layer. From input to hidden layer, some weight is going on. That weight, that initially I am taking as some random number, and this BH is nothing but bias going to hidden layer, and W out is nothing but outside from the hidden layer, whatever output you are getting, that whatever output you are getting, very so output you are getting from the hidden layer, that you have to take. So that is nothing but W out, and that is nothing but B out, bias out. So first I'm initializing all these things, and then this step is whatever I am going to do in my layers, whatever process I already told you to happen, that process. So first, suppose these two my input layers, and these 3 are my hidden layers, and this is my output layer. So I'll connect each and everything here. So this is my basic neural network. So in between here, this x1 and x2 are my input. So here that w1 and w2 are my weights, and I am going to give a bias here, let's say b1. So whatever input here it is reaching, the input will be x1 w1 plus bias b1. So that will be given to this, let's say this is h1. So this is the input getting to this particular neuron. That's what we are doing here. So here np dot x and input and weight. So that I am going to store in some variable, and now this variable will be added to bias, whatever bias I am giving. So all that information I am teaching to mission. Now after doing this thing, that I stored in some variable hinp. So this one, now I have to make it to activation function. That input should be given to activation function. So Now that is given to a activation function of sigmoid. So now the output layer, output which is coming from this neuron is nothing but this complete after activation function, whatever value it has, and of course the weight out, this complete thing, this complete thing, and and the activation function result. So that too will come as a function, and again here, again whatever coming here, let's say this is some y. So for this y, again we will add some bias and some weight. Let's say this is y2, w2 and b2. So the same thing here I am taking. So whatever coming here after activation function, whatever coming here, to this I am adding bias. So this will be stored in another variable, and this variable again I am taking, I am giving to activation function. So this is the meaning of this code. So whatever process I am doing there, the same thing I have represented as a formulas, and I am teaching to the machine. And this is nothing but, so uh, once the everything is over, at the output, the output is no y is predicted, mission has predicted some output. So the y prediction we got, and we know already the actual values we have already are y 89, 88, some values we have. So we will take the difference between our y prediction and that actual value. So that what's this meaning. So this is nothing but, this is actual value and this is the value which is predicted by our mission. So this is our mission. Let me zoom it. So this is the meaning of so this is actual output which is coming, which is we have in our data set, and this is the predicted output. So the difference will be stored in some variable evo, and then we are we are using the gradient descent algorithm to minimize this loss. So to minimize the loss, already I told you we have to take the derivatives of this activation function or gradient descent algorithm to take the derivatives, and whatever values we are getting, then again that multiplied by this output. The gradient output, the gradient, whatever value it is coming, that will be multiplied with our output. So that is our final output. Then this output will be feedback to our first hidden layer. So fed back to our first hidden layer, then depending on this value, our hidden layer will decide what is the weight values to be updated. So this line is to update our weights depending on the derivative value, depending on the loss value. Our derivatives, our hidden layer will update, our gradient descent near our hidden layer will update the weights. This is what this code means. Then so all these codes are like whatever we have learned, the formulas, the same thing here I have uploaded. And these are how the weights are updated. So here this is the weight whatever finally we got after gradient descent algorithm. This is the weight we have got, and then this is multiplied by the learning rate. So learning rate already we have given at the starting, that is a hyperparameter out from outside, from external we are giving some value, so that is a hyperparameter. So I told you model parameter and hyperparameter. Model parameter is like weights which are going to update from the training, but learning rate is a something hyperparameter which we are giving from outside. So it is multiplied with our learning rate.
So depending on this learning rate, this value will be changed and is stored to this W out. And again, the final WH from the hidden layer, it should be again passed the information to output layer. So this is the output layer. Again, the same thing happen here. It is multiplied by learning rate. With some learning rate, it will learn more, and then it is passed to the output layer. And next thing is the printing values of what is my input, what is my output, and what is my actual output. So if you see this, this input, you have all normalization values. This thing we have did the normalization for our features, but starting we have considered the features as 2,9, but here the value is normalized to some a consistent range. So this is called a normalization. These are our actual values. We have normalized this 92 divided by 100. So each value we have normalized with 100 at the starting. So this is the normalized values of our actual actual prediction, and these are our predicted outputs. So if you see the difference, there is not that much difference. So these two are almost equal. It is predicted as 72, but we have an actual value 86. So after some 9,000 epochs, we have considered some 7,000. So after 7,000 iterations, there is not that much difference between these two. Okay, our machine is almost predicting well. If you train more, it will predict more. So that is the this is the basic structure of artificial neural networks. Hope you understand. This already yesterday we have shared the link. So now we'll move on to the next concept of today's CNN. So already we have ANN. Artificial neural networks are doing well. Just now you saw that our artificial neural networks are doing very great. But why we have to come across to CNN? That is the main first question arise in everyone's mind. So what's the main difference between ANN and CNN? Just I'll take an example of some monkey picture I have. A monkey picture I have. So how a artificial neural network will see that monkey picture, and how that will be given to a machine, and how that machine will learn that that is a monkey picture. As you know, some features as a deep learning, already you have known that the main difference between machine learning and deep learning is feature extraction. So of course artificial neural networks will extract some more features, like the eyes, other than whatever global features like eyes, nose, and something. The artificial neural networks will extract some more hidden features of some black color under the eyes, some skin color is changed somewhere, or some hair is there on that face. So all that hidden features it will extract from the monkey image, and then it will guess that, finally it will guess that it is a monkey. But what will happen in ANN is, suppose I have a picture of monkey like this. Suppose I have a monkey of picture. So anything, any picture, how a machine will work is like it will divide that picture into some pixels. So it will divide this pixel. So let's say monkey I cannot draw here. So I'll take a number of 9. So some handwritten image of 9 is there. This is the my 9 image. Now I want to ask the machine to predict my 9 image. So 9 image will be like this in my pixels. So now artificial neural network will consider each and every picture, every pixel, and it will take this pixel in one node, and this pixel in one node, and this pixel in one node. So let's say here some 24 into 24 pixels are there. Let's say it is a 24 into 24. Normally it is 64 by 64 in general.
So 64 by 64 means total how many nodes will come? 64 into 64. 64 into 64 nodes will be generated in the input layer. But in this 64 into 64 nodes, almost these nodes are always empty. In every iteration, almost these side nodes and these side nodes will be almost empty. So what will happen? That is like, wasting the pixels unnecessarily every time. If we are doing some epochs means 7,000 times you are doing means 7,000 times it is wastely processing from that nodes. It won't replace anything. It won't do anything on that particular node, because ANN don't know that we can drop that particular node. It will iterate each and every time that thing. And suppose that is the main problem of ANN. It won't reduce the things. It will whatever we have in that, it will extract that all the features, and it will create a one dimensional nodes. So, but if it is a simple picture of monkey, it is okay. But if it is a very large picture, large data set, so then what will happen? That will be, computational speed will reduce, and storage will not enough, and of course the error percentage will increase. The machine cannot able to predict clearly. So then CNN comes into picture. So CNN almost works like a human. So how human will identify a monkey? So if you see a monkey picture, how a human can identify? So we cannot see the unknown things of on a monkey face. First, whatever we observe naturally as our human intelligence, we will observe whether the monkey has a black color under the eye. So only we'll concentrate on that particular feature. The remaining around the same color of skin we don't see. Automatically wherever you see the black color under the eyes, so automatically you can able to recognize that is a monkey. So the same happens in CNN also. CNN also will try to extract the exact features, whatever features you need, that it will try to exact that features, and it will try to reduce the unnecessary features. It will reduce that. So feature extraction will happen same like ANN and CNN, but in CNN the extraction will be done a very less. Important features only it will come across, and then it will pass that information to the input layer. So that we call it as a feature engineering. That will happen in CNN only. So that is the main difference between ANN and CNN. And CNN will consist of, so first I'll show you how a CNN layer will be, and then we'll discuss one by one. So this is a basic CNN structure. So here I have a picture of giraffe. So instead of taking somewhat here which is unnecessary, so here this scenery here, the color is same. So any picture can be stored in 3 dimensions, that we have seen in the first day of deep learning. Tensors. So any image, the image size will be stored, image length and height will be stored, and of course one more extra feature will store for an image is the grayscale, the color. So the grayscale will be divided into 0 to normally 255 pixels. Will have 0 to 255 pixels. So in these pixels, depending on that number, it will be decided. So here if you see, the pixel value is same for this particular part. So this particular part of the feature pixel value will be same. So CNN will not concentrate on all these particular features. So these features we don't need to identify a giraffe picture. So what it will take, the most important is this part and this part and the legs part. So it will take only that part. So then it will pass on to another. Then it will pass on to the next operation. So this part is called a feature maps, feature extraction. So in feature extraction, we'll have a kernel. Kernel is nothing but a filter. So to reduce these features, I mean to identify what are the perfect features, we will use kernels in CNN. Kernel is nothing but, in simple words, filters. So we will use a filter and we will extract what are the important features to identify a picture. So we'll use kernel. So here I have used a kernel on the legs. So that kernel will be mapped to convolution matrix. So we will do an operation in CNN is convolution. So we'll take that filter and we'll apply that filter to we'll keep on moving that filter uh, on that complete image. Then a matrix will be mapped. That operation we call it as a convolution. Wherever the particular leg is there, that we have to identify. That is the work of filter. So that operation is convolution operation, and then it is reduced again by pooling operation. Pooling is nothing but, if I have 100 into 100 pixels of image, by doing some operation, I'll reduce that into 50 into 50. So reducing the dimension is pooling. Then again, I'll apply convolution operation, means I'll take one more filter with a bigger filter or small filter, whatever maybe I'll take. And again, I'll move on that filter, that kernel on that complete image, and wherever exactly that feature is there, that again that operation, convolution operation I'll do, and again I'll apply pooling. So finally you can see from this much bigger image to I got only this much simple slides. So here the almost wastage is completely removed, and finally I got only these important features. Now these important features I'll make here, I have some 10 dimensionality. This 10 dimensionality I made it as a one dimensional matrix. So only one column I'll have. So this one dimensional matrix is called flatten. This operation is called flatten. Flatten. So now this flatten matrix will be given to each node. So here suppose I have some 100 into 100 pixels. If I have to do the same picture with here we have to connect these nodes, means I have to do it 100 into 100. So 10,000 nodes I have to create, and I have to pass each and every information to each and every node. To avoid that, first I have worked on the features, I have reduced the features, then I made as a flattened layer, and then that layer will be connected to input layer. The remaining thing is same. Then from the input layer we will connect the hidden layers and one output layer, and in between the weights we will add, bias we will add, and of course activation function we will add, and of course the loss function will calculate. See, probability here we are calculating whether it is a horse, whether it is a zebra, or whether it is a dog. So wherever the most probability is there, because here we are using softmax activation function, so it will calculate the probability. So wherever the maximum probability is there, that we will take as a output. So this is what happens in CNN. Now we'll see each and every this operations in detail. So CNNs are a class of deep learning algorithm that are particularly used for image classification. Mostly, in most of the cases, the application is for image classification. And it has consist of few layers. The first layer is input layer, and second one is convolution layer. So I'll explain the convolution operation with a simple example. So let me take some image of the same 9 I am taking. Let's say I'm taking a handwritten image of 9 like this. So I have divided, the mission has divided this into some pixels. So these are my pixels I have divided. Now for the kernels means filters, I have to consider here. I am considering 3 filters. So this is my one filter. So this is my one filter. So this filter will consist of all round. So this part, it consists of a filter. So second filter is consisting of something like this one. So second filter I am considering like this. So it will consist of a vertical line, a vertical line. So let's say this is a vertical kernel. This is a round kernel. And my third filter I am considering somewhat here some curve. Some curve kernel. So these are my filters or kernels I have considered first. 3. So these kernels can be any number of matrix. Like here I have considered 2 by 2 matrix. Here I can consider 2 by 2 or 3 by 3 matrix. Any size you can consider depending on application. Now this filters will be passed on each and every complete image. It will pass on this complete image. Let's say if I convert my 9 into the matrix, so what I'll get, wherever I don't have 9, wherever I don't have any image, then I'll mark it as a -1, -1, -1. Suppose here I have a image, so I'll mark it as a 1. So -1, -1 and 1, -1, -1. So let's say like this I have marked. So here -1, -1. So only this part I have that image. Now my filter I am considering. My first round filter is here, this is -1. Here image is there 1. Here image is there 1. Here image is not there, -1. So like that somewhat I have considered 1, -1, something -1, 1, 1, or let's say this is -1 and 1, 1, 1. Let's say this is my round filter. So convolution operation will do a dot product between these two. Now dot product will be like, so what I'll get dot product, you already you know in your matrix operation. So this will be multiplied with this number, this will be multiplied with this number, and this will be multiplied with this number. And we will get in the first row of our matrix will be the summation of these 3 and these 3. So let's say the value is somewhat like 0.11. Why I am getting float here? After summation, dot product means again I have to take the average. So I have to take the total is here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So something if I get 1 by 11. I have to take the average of the value. So let's say I got 0.11 here, 0.2 here, some 0.6 here, 0.01 here. Let's say all these values I got by applying filters. So this is only when I apply a round filter. So similar things I'll get when I apply a vertical kernel, when I apply a curve kernel. So this thing I call it as a feature map. Feature map. And this operation of dot product is called a convolution operation. So I hope you understood. This is the convolution operation and this is a feature map. So like this, I will get so many feature maps. So suppose it is not 9. Suppose I come across through 6. So 6 means the filter, when filter is checking the throughout the image, where that ones comes, where that feature maps comes in this part at the end. At the bottom, I'll get all the ones. So in my feature maps at the bottom, I'll get complete one because there is a map, there is a image. If I come across through 8, if I want to predict number 8, so number 8 means I'll come across through my filter will predict one round here, and one round at the bottom. So if you two ones are coming in my feature map, then my convolution operation will say that that is a 8. So like this, the filter operation will occur, and this is called convolution operation. Then I got some feature map here. So let's say here some 0.9, some 2, and something 0, and 0.1, 0.5, 0.4, and 0.2. Now this is my feature map after calculating, after doing with a one filter and the convolution operation. So after doing all, after applying all the filters on the complete image, so you will get so many feature maps. So 3 feature maps you will get, and you will aggregate all these 3 feature maps, and finally you will get one feature map. So after getting your feature map, now the pooling, operation will happen. So suppose now this is my, let's say I have got my final feature map is like some 8, 9, 3, 4, 1, 2, and 2, 3, 4. So now I got my feature map is like this. This is my feature map. Now pooling operation will reduce this dimensionality. See, here the dimensionality is 3 by 3. 3 by 3 matrix. Operation will reduce the dimensionality. So there are two types of pooling operation. One is maximum pooling and average pooling. So if you consider maximum pooling, so it will consider some strides. It will consider some 2 by 2 matrix. You have to apply that whether that is a 2 by 2 pooling or 3 by 3 matrix for the pooling. So here if I consider 2 by 2 matrix, so in this 4 squares, whatever may be the maximum value, that it will consider as our feature. So 9 is the maximum value in this particular slide. So it will take 9. Again that will be moved to one step next, and in this 4 again 9 is the maximum value, so I will consider 9, and it will come to the bottom. So in the bottom the maximum value is 4, so it will consider 4, and next it will move. So in this again the maximum value is 4, so 4. Now the feature map will be reduced from 3 by 3 to 2 by 2. 2 by 2. This is how we reduce the dimensionality. If you are considering the average pooling, so it will do the average of all these 4 numbers and it will take that value here. Again the dimensionality will be reduced from 3 by 3 to 2 by 2. So this is how we will do the pooling operation. And once you do the pooling operation, then again if the matrix here, if it is 2 by 2, then I can flatten this directly, like here my 9 and here my 9 and here my 4 and here my 4. Then I can apply directly. I can make that 2 by 2 matrix into 1 by 1. Directly I can use 4 nodes. But if it is in real time, it won't be like 2 by 2. It will be very bigger. So again you have to apply the same convolution techniques here. Now instead of taking a the filter, so I'll consider the filter is only one. Only one, a small filter I'll take, or I'll increase the filter size. Either I can update that filter. From the starting level, I'll update something, I'll change something in that filter, and I'll take again filter. So that filter will extract more features. Whatever still in this 9 also, some features may not we need. So again it will go through complete image. Whatever image we have, it will go through complete image and extract some more features. And again we'll do the convolution operation, and then whatever feature map we are getting at that time, again we'll do the pooling operation. So finally our aim is to reduce that completely to 2 by 2 matrix or very less dimensionality of the matrix. So once you can know that is enough, the size is enough to do the dimensionality, then you go for flattening. So these are the operations we do in our CNN. These are the basic operations. And here, while doing pooling, we are moving one by one step. So this filter is moving first here, then it is moving next to one step. So this thing is called stride. So one stride means only one step we are moving. So if you are moving, you are jumping from here to here. Suppose I have one more thing. So now this filter is completely jumping from here to here. So it two steps it is moving. So in that cases, I call it as two stride filter. Two stride filter. This is one stride filter. So that is a type of stride. In some cases, after doing the feature map, maybe for pooling operation or something, the data is, it is not enough. Whatever matrix I am considering here, maybe that is not enough. I have to the matrix size is not same with our convolution matrix, maybe filter. So in that cases, I can't do any matrix operation. If I want to do a matrix operation, either cross product or dot product, the size should be same. So for that, without losing the data, what I'll do, I'll keep some more. I'll keep some more. Suppose this is my data I have. After pooling, this is my data, but this size is not enough to do my convolution operation. So I cannot lose my data. What I'll do, I'll add some more layer here. Maybe this is some 3 by 3 matrix I have. So I have to make this my 2 by 2 also to 3 by 3 matrix. In that cases, I'll add one more thing and I'll fill this thing with all zeros. With all zeros, I'll fill. So if I fill with zeros, the value will not change. Here the data set will be same. The whatever values we have calculated that are same, but just we are adding some extra layer with zeros. So this operation is called padding. So in CNN we normally do always padding to reduce the data loss. So we'll just add one more layer to make it same size with whatever operations we want to do. So for that, we don't want to lose the data. So in that cases, we'll just add a layer with all zeros. That operation is called a padding. So these are the basic concepts of CNN. So it's already 7:18. So these are the maximum concepts of CNNs. Now we'll take the quiz and then we will see some medical images analysis using CNN. A hands-on on medical images of CNN. Now we will share the quiz link now. You please, all these concepts will be there. You please try to attempt. Now we will share. So welcome back, and hope you can able to attempt the quiz session. Now you'll see the hands-on of CNN. Zoom in, zoom in. First, we'll see one CNN with. So here for this program, I have downloaded the X-ray images, different X-ray images I have downloaded, chest X-ray images, and so that images for training and testing, training, I have considered that images from Kaggle. So from Kaggle dataset, I have considered. So first, anyway, it is defaultly installed, but here I have installed Kaggle API. That Kaggle API I have installed here. Run it. So from that Kaggle, So Kaggle API I have installed. From that Kaggle, I have considered all the different type of chest images. So this link we will share you now. So once I explain, while explaining that link already we have shared you. So while explaining, you please go through that link, then you'll understand better. So first thing I have installed that Kaggle, just images I have downloaded. Then from that Kaggle particular this chest X-ray pneumonia images are there. So I have downloaded that images. So this images data set I have downloaded from the Kaggle. So that particular data set I have considered, because most of the people are asking me to do the CNN on medical images. So I already did one CNN project on normal MNIST. I mean handwritten images, whatever I have explained, that 9, 8 normal handwritten images. But now just few people are asking me how to do that images classification. So I have considered this just images. So now I have downloaded this data set I have downloaded. Now my chest data set here, this is downloading. And now normally whatever image data set you are going to download from Kaggle, all the data set will be in zip format. So first that zip format any machine learning or deep learning algorithm will not able to understand. So first I have to unzip that. So first I'll unzip the chest data set. So that's why I have used here unzip. And once I unzip the data set, here in Kaggle, already this data set is divided into some training data set and testing data set. So the training images will be given and testing images already divided in that default data set. So I need not to again divide that too. So directly after unzip the data set, now I have imported whatever libraries I want for CNN. So here see for CNN, first I have imported my TensorFlow as I am doing all my neural network things. And then from Keras models, I have imported my sequential, because for the neural networks, yesterday I told you either I can make it as a layer combination, a combination of different layers side by side, or you can implement everything from an basic raw, or you can import that layers in some API. So any three methods you can follow to build the neural network. So here I'm considering the sequential model. I just want to make it a layer by layer combination. So I have imported the sequential. For CNN, I need convolution operation, pooling operation, flatten, and dense is nothing but after doing all these operations, after doing the complete feature engineering, then we are making that into a one-dimensional array, and that one-dimensional array I have to connect to my neurons. So after connecting that input neurons, that input neuron information should be processed to hidden layer. So that information, each neuron in the input layer should be connected to each and every neuron of the hidden layer. So whatever information it is there in the input layer of a node, that information should be passed to all the neurons of the hidden layer. So each and every neuron will be connected in 3 layers. Either it may be an input layer, hidden layer, and output layer. So that is called a dense layer. Dense layer is nothing but fully connected layer. Everywhere, every node will be connected to the other node. So that is called a dense layer. So here dense layer I am going to import and drop out. Dropout yesterday we have discussed. It is a one type of regularization. So dropout means yesterday I told you like an example, a basketball team. So at the starting, some of the best players, I am going to make it them sit, and I am asking the a medium level players to play. So at the end final match, everybody will have the competency, or everybody will have the strategy to win the game. So that's what we do in our neural network also. Dropout means some part of neurons I'll make it unable, I mean, and make it ideal, so they don't do any work in for a particular time. So I'll give that amount, how much amount of neurons I want to be a ideal state. Then after after few operations or after few iterations, I'll make them participate actively in that workout. So in the meantime, the remaining neurons will be able to understand the concept and able to analyze the data. Then they'll get that much strategy like these neurons. So that is what happens in our dropout regularization. And next thing, I am downloading that pre-processing module. In that, I am down importing this data generator. Image data generator is nothing but uh, if suppose for making this convolution operation or pooling operation, I need a few more images to for training. Maybe I need some 10,000 images, and but I don't have medical images, means maybe from the hospitals I may not get some 10,000 images. I got only 5,000 images only. So from the 5,000 only I have to do the CNN operation. But that 5,000 images may not be efficient to do that CNN operation. Then what I'll do, I'll apply some techniques on that. So different techniques I'll apply, like data augmentation. So I'll rotate that, I'll slide that, I'll minimize that, I'll zoom out that. So some different techniques I'll operate on that particular image, so without changing the meaning of the image. So I won't change that image. The image will be same. Some operation I'll do. So I'll make the same image into 10 times, 10 different images. Same image will make that into 10 different images. So that what the image generator will do. So it will create different images. So that I have imported here. And, to visualize the results, I have imported matplotlib. Then first thing in CNN is, first we have to decide what is the image size we are going to use. So in one of the main important thing in CNN is to make sure that all the images whatever you are processing for training and all the images you are processing for testing should be on the same size. It should be on the same size, then only the accuracy will be more. If it should not be in a different images. If it is a different sizes, then the machine will be confused and it cannot able to process the data. So first I'll fix that image size as 150 into 150. Randomly I have fixed the image size should be, my width and height of the image should be 150 and 150. This batch size is nothing but how many images I want to process for an one iteration. At first step, how many images I want to process. So here I want to process 32 images at a time. So for the first iteration, for 32 images I have to process at a time. And that is one batch. So after completing the training of one batch, then again the number of 32 images I'll take, and then 32 images so that batch 2 will be processed. So machine will learn about the images in terms of batches. So how many batches we are giving. So batch size is 32 here. Now next here I am doing the data augmentation and some pre-processing on training and testing data sets. So here I am for that data augmentation. I already told you I have imported the data generator to create different images, and here I am telling that mission some type of data augmentation operation. So here I'll rescaling the image and shear the image and zoom the image and horizontal flip, that I'll do on that images. Some operations I have considered here. So each and every one I have represented a value. So this 255 is nothing but the pixel range, the color scale range. So from color scale will be gray, RGB range will be like 0 to 255. So I have considered a float value, and each pixel I am going to divide with that 255. So whatever value I am getting, that I'll create as a picture. I'll rescale it. And shear range I'm considering 0.2, and zoom range, maximum zoom or zoom out, zoom in, that maximum range I'm considering as 0.2. Now horizontal flip. So horizontal flip or up and bottom, that I am going to make. That will happen for each and every image. So some data augmentation techniques I am doing. And on test, that will be on train images. This will be on the train images. Train images, I am doing all these things. But on the test data set, I am not doing all these shear horizontal flip. I'm not doing that many operations of augmentation because I don't need for testing. Only testing images, a few things, few operations will be enough. So I'm just doing only rescale. Only I make sure that the size should be same. That's it. So testing only, I have to pass a more data set. So that's why I'm doing so many operations on the test. So this is my test data set. Now, after doing all these operations, now I'll load the training data. So this training data, from the train generator, I have did so many operations. So everything is stored here. This is my data set which I have considered from my Kaggle notebook. This is my data set. So here I am giving target size and batch size for testing, and class mode I am giving as binary, because here my in the label just I have to predict whether for a chest, from the chest X-ray, whether I have to predict whether the chest X-ray is a normal X-ray or it has a pneumonia. So either 0 or 1, yes or no, 0 or 1. That's what I have considered here. We'll run it. I have loaded that. So here found 5216 images belong to two classes. So these two classes are nothing but either few images have a um, normal chest, and few images will consist of a pneumonia something X-ray. So that two classes we have. Now after training that, after doing that, for the validation purpose, again this is I am defining for training data set. Training data set I am defining this width, height and batch size. Already we have given that at the starting the values, and for the testing also I am giving the same image height and width and batch size and binary. So how many elements I have to, how many images I have to pass at one iteration. So found 16 images belong to two classes for the testing. So testing I have kept 16 images. This is just for training purpose, for evaluating I have now build the CNN model. How to build a CNN model now? After training and test data sets, we have divided and we have we did some pre-processing techniques on that data sets. Now I have to build a CNN model. So first I have build a sequential model. Sequential model. In the first layer, I am going to uh, uh, I'm going to access is a sequential is a convolutional operation. So first operation I have to do a convolution operation. Since here my batch size is 32, so 32 I am considering here. This 3 by 3 is nothing but the kernel size, kernel dimensions. I already told you convolution operation starts with the filters or kernel operations. So how much kernels here I am going to consider? So here I am going to consider 3 by 3. 3 by 3 kernel here I am considering. So this is 3 by 3 matrix I am considering. My kernel filter size is 3 by 3 and my batch size is 32. And here the input shape I already given, like this is 150 and 150. This 3 is nothing but the color scale. So when we are discussing the tensors, all the images will come under 3D tensor. So this will tell the color. So RGB, grayscale image, that color pixels, the color different variations, the reverse resolutions it will tell. So 3 is nothing but RGB. So it will be given by the input shape, and here I am activation function I am using ReLU. Why? Because ReLU means already I told you, whenever it is a positive value it will consider. it will process. Otherwise, it will just make it as a 0. Rayleigh activation function, whenever some positive value is there, then it will process that. Otherwise, it will just give 0. So Rayleigh activation function always gives 0 comma maximum. So that's why I have considered the activation function as Rayleigh. Then the next layer is maximum pooling. So here I can consider average pooling also. Now I am considering the maximum pooling. So maximum pooling and pool size here I have considered 2 by 2. So I'm decreasing the kernel from here to here. So 3 by 3 matrix here I'm doing. I'm convolution operation here I'm doing. Now I have considered the pooling as 2 by 2. So after coming here, the matrix will be some 2 by 2 matrix with only the maximum values of features. So I have different features maybe. In that only I'll have the maximum, whatever the maybe the maximum feature value, that value will be considered here and will get a 2 by 2 matrix. Then again, I am going to apply one more filter, one more convolution operation here. Now, if you see, if we see this convolution operation, here I am considering 64. So here I am considering 32. Here I am considering 64, the batch size. 64, no, 64 elements are there. And now my filter size is 3 by 3. So again the pixel size I'm decreasing. I'm considering that 32 pixels into, again I'm taking that as 64 pixels. So very minute pixels I am taking. So my filter will able to extract the inner features also. Moreover, hidden features, hidden elements are there, that also my filter can able to extract. That's what I'm increasing here. And again, activation function I am considering Relu here because I don't want any negative values. I just want to continue with the positive values. And the pool size again I'm considering 2 by 2. So one more convolution layer I'm going to apply. So here again I am increasing the value of the pixel. Uh, the increasing the value of the pixel is nothing but I am decreasing the pixel size. So the filter will able to more predict the hidden feature, whatever the very minute differences in the image also it can able to predict. So I'll increase this. Again I'm taking the filter size as 3 by 3. And now my activation function is ReLU and maximum pooling size is 3. So here I have applied 3 convolution matrix, 3 convolution layers, and then I have considered flatten. So whatever values I got here, that will be converted in 1D matrix here. Now my dense network I have considered 512 because it is 255 into 255 pixel size, and R normally that will be pixel is 64 into 64. So the maximum range I am considering my dense network, the completely fully connected network. I have considered 512 neurons. Again I have considered the activation function as ReLU. Now dropout is 0.5. 0.5 means 50% of the nodes I am making ideal in the starting level. In the starting initial level, 50% of the nodes I am making it ideal and the remaining nodes should be activated. So that's what the meaning of dropout. And here this is the last output layer. So here I am considering only one node. That one node will tell you whether the X-ray will be a normal X-ray or pneumonia X-ray. So that is what this one. And here the activation function I am going to take sigmoid. So sigmoid will tell you between 0 to 1. And it will create a threshold value. So I'm taking the activation function as sigmoid. Here you can take a softmax also because it is just binary classification. Only I have to classify between whether the X-ray is a normal chest or a pneumonian chest. I want to classify only in that too. So I have only two predicted variables. So it is a binary classification. I have considered sigmoid. If it is a multi classification, then we'll go for softmax. So this is how we build a CNN neural network. We will run it. Then further compile. Then further compile as it is a binary classification. So yesterday we have discussed all types of loss. We have when you are going to use if you are doing a regression problem, the loss functions will be MSC, MAE, all these things. When it is a classification algorithm, the loss functions will be binary classification, cross entropy, all these things. So here it is a binary classification. So the last function I am using as binary cross entropy. Binary cross entropy. And optimizer I am taking the Adam. I can take RMS prop also. Anything you can use. And metrics as it is a classification problem I am using accuracy. So these are the compiling things I want to analyze my model. Now then train the model. So whatever I am going to train, whatever I am taking that images, I am training that images, everything I am going to make it save in some part of history, some variable like history. And here first generator, train generator generated some extra images, so that I have considered, and epochs I have considered 10. So 10 times the complete cycle should be happen. So 10 times the complete 32 batch size or 64 batch, 128 batch, everything should be processed 10 times. Each sample should process 10 times. That is the meaning of epoch. So each iteration will be completed and then each cycle will be completed. Then that is called one epoch. Like that it should happen 10 times for each and every example. And so see, it is taking epochs. So it will take much time. Yesterday I told you machine learning will compile fast, will train fast, but deep learning will take so much time to compile. Deep learning will take so much time to train, but the accuracy level will be good. So it will take so much time. Definitely 163 are there, and still this is the first epoch. Like this, it has to complete the 10 epochs, and of course it has to give the value. So without completing this, we cannot run other things. We will just see the what is there. So after training, I am going to save my model here. I am going to save my model because I just want to check if for some random X-ray image is there for me. Then I want to check whether the particular X-ray is a a normal X-ray or a pneumonia X-ray. So I want to save my model in somewhere in just in model. Then I have plotted whatever accuracy, model accuracy, epochs for the training thing. I want to plot the graphs. So here I have used a plot and title I have given as model accuracy, Y label, X label. So this is my model accuracy. This is my model accuracy. So if you see this model accuracy graph, this blue color is nothing but the training accuracy. So on the y-axis I have training. These are the epochs. So for each epoch, if you observe, the training accuracy suddenly fall down and reach to almost zero, and again it is getting up. The blue color thing is a training accuracy, and this orange color is a validation accuracy. So if you analyze this, what do you know? This training, it is completely abrupt. If the model is learning properly, then the curve should be somewhat like a linear curve, somewhat like a consistent curve like this. Of course, validity curve is a bit better, but your accuracy curve is training accuracy is suddenly dropping and suddenly rising. So this means that your data, whatever you have supplied data, that may be overfitting. So suddenly the machine is learning very, very highly for a batch, and for the next epochs, it's completely dropping down. It don't know anything. It's not able to immediately learn something for the next epochs. Again, when you supply another batch, it is learning very properly, very high. I mean, very good. So very it is reaching the highest point. Then for the next epochs, it is completely reducing. So after some time, again it is increasing, and in the starting of next batch, it is completely decreasing. So it's just like maybe there may be more noise is there in your data set, or maybe overfitting of data is going on. Some issues will be there. So maybe you are not pre-processed correctly. So so much duplication is there that your machine cannot able to predict. So all these operations are there. That's what your accuracy is like this. But when after training completely, your machine is very good in predicting. So this is the accuracy of your prediction curve. So it is a bit linear. So of course it is starting, it is decreasing, accuracy reducing, but then later after some time, it is continuously increasing. For each epoch, it is consistent for some time and then it is increasing. Of course it is increasing. So your machine is able to predict correctly. It's generalized to new outputs. But in the training itself, something is some regularity, some regularization, something is missing. So that you have to see. See here still it is training. It's 129 still in epoch 1. So it will take time, so much time. So, so this is the curve between the training and validation losses. So if you see here, see again the blue color is the training losses. So the loss is completely abrupt. So for each and epoch, so for one epoch, after completing this one iteration, it is suddenly increasing the loss, and after training sometime, it is suddenly decreasing to zero. Suddenly minimizing and suddenly increasing. So this is the problem of overfitting actually. Overfitting or some noise is there. The data pre-processing we have not done correctly, or we are not the dropout amount, whatever dropout amount we have considered, that is not correct. That we can change and we can check this. But validation is proper. The validation, after the starting level, the loss is increased very much, but later it is decreased to minimum. The loss is decreased to minimum, means that your model is very good in predicting. But this is not no, acceptable. The training should be a very good for any model. Now this is the evaluation. Once the training is over, how you will evaluate this. So as it is a classification model, so I am going to take only test accuracy. So my test accuracy is 89%. So I cannot run this because there the training is still not over, so I cannot run this all these things. So here this thing is my test accuracy is 0.89. So 89% accuracy I got. Now if you want to see how what type of images I have considered from the Kaggle, so that images I have did some, these are the images I have considered from Kaggle. These are the data set. So there are two what no data set I have given to my model are like this. These images I have given. So few images have some pneumonia images, and few images, just images, are normal. So these are the few images. Here I have given how many numbers you have to show. This is just like a matplot library, visualization library. So here I have given the labels normal and pneumonia. So just 9, some 9, 10, 9 for indexing. It should be a row of total 9 images I want to see, and for a row I have considered 3. So these are the images for your training images. Now my aim is, now I have built the model and I got the accuracy of almost 89%. Now my aim is, for any machine learning model, if I give a new input somewhere from somewhere, whether the model can able to predict or not. So deployment, whether it can able to predict or not. So here to check that new input, I have considered this image from just Google. I have downloaded that image, a normal Google image JPG. I just typed like some Chester X-ray image. So I have downloaded some X-ray image, And here this thing is whatever model we have saved in our previous, our previous model. This is our saved model. Now I have called that model, and this X-ray image I have considered from Google. So I have given the path here. From my computer, I have given the path here. I have considered. Now I want to check whether my machine learning, my deep learning model can able to predict that image as a normal or pneumonia or not. So for that, before directly giving that picture, first I have to pre-process on that picture, because I have to make that picture into the same dimensions as whatever I have trained my model. Whatever data size of my images, in the same size I have to give my test image also. So first I have pre-processed something. I just rescaled with the same whatever amount I am taking at the starting for training data. The same thing I have considered here also, and rescaled my image. Then if my whatever image, whatever model I have considered, if that is the prediction is above 50%, the accuracy is above 50%, then call it as pneumonia. If not, I'll make it as a normal. So once you run this, this is my image actually I have considered from Google. So it is predicted like, yes, this picture is a pneumonia X-ray. So this is how a CNN will work out, and ANN also can predict, but in sometimes if the grayscale and the color image is very clumsy, or else if the resolution is not well, then it cannot able to predict. But if still the resolution is whenever I have considered this image, that is very light resolution, then also CNN can able to predict whatever may be the image, because the CNN will able to extract the hidden features. So this is how we'll do a CNN on images. This I want to see whether that image is a normal or a pneumonia. Just a Google image this thing. So it is predicted as pneumonia. So this is a one type of CNN network on medical images. We'll see one more code on same CNN. That is some CNN on MNST, a basic simple code. Same CNN, but on a basic MNIST. So MNIST is nothing but the handwritten numbers from 1 to 9 in different ways. And some people may write like this, and some people may write in different ways. So that 9, maybe someone may write like this, someone may write like this, someone may write like this. So as a humans, we can able to understand all these things are 9. But a machine cannot able to understand that this is 9 or this is 9, this is 9, this is 9. Machine cannot able to understand that. So we have to teach that machine that all these things will be come under 9. So this is the project what we do in MNIST. So each and every number from 0 to 1, 0 to 9. So whatever may be the number, depending on that some features, the machine has to able to predict the correct number. So that is the project of MNIST. So for that, here we just consider the same whatever layers we want, and convolution layer, maximum pooling layer, flat and dense dropout. So these things I have imported from Keras library. And then data set directly I have considered MNIST. MNIST will consist of some 70,000 of images. And in that 70,000 of images, each pixel, each image will be like 64 into 64 pixel images from 0 to 9. So I have considered, I have directly downloaded that from Keras datasets. And here I have given to the mission that this is my exit train, this is my Y train. Exit test will be the from 0 to 9. So here the classification will be the different variables will be there from 0 to 9. So 10 variables will be there. So this comes under multi classification. It's not a binary classification. First thing is, whenever you are working with images, first thing is you have to normalize that data set. So first I'm normalizing, since it is a pixel value. I mean, RGB scale is from 0 to 255. So I'm dividing each and every pixel with that 255 to make it normalized. Visual keras is nothing but that actually no need. Just to make it a beautiful thing, I have downloaded Visual Keras. Visual Keras will show you the architecture of the neurons. That actually we need not to do that. It will show how that neurons are happening, how that neurons are building layers by layers by layers. So this is the final CNN, whatever we are going to build. So first I have built sequential. Then here first I have considered only 32 neurons in my, 32 features only, 32 dimensions only I have considered. Then the size of the matrix of size of the filter I have considered is 3 by 3. Then ReLU function I have considered. This is nothing but 28, 28. One is only one, color scale I'm going to consider, either gray or white and black. So one scale I'm gray scale I'm considering, and 28 is the height and width. And again I'm increasing that the size, so decreasing that pixels to go into the depth of the this thing. So 64, and here I'm going to consider 120. 64 here. Two convolution operations I am going to use, and then I am flattening the 2 by 2 matrix into one dimensional matrix. I'm flattening. Then for my this flattening matrix, I'm going to connected to my neural networks. So in dense layer, I'm going to use 128. So here dropout, I'm considering only 20%. So 20% neurons, I'm going to make it ideal. And it is a multi-classification at the output layer. Output layer here, I'm considering 10 neurons because the variables are from 0 to 9. So 10 neurons should be there. So in the output layer, I'm considering 10 neurons, and probability, I just need to calculate the probability. How much probability is there that the new input is a 1? So that I have to calculate. So I have considered the activation function for softmax. And for the compile model, as it is a classification but a multi-classification, so I am using a sparse categorical cross entropy. In the previous case, if it is a binary classification, the loss function we have considered a binary cross entropy. Here it is a multi-classification, so we have considered a categorical cross entropy, and optimizer you can consider anything, RMS prop or Adam. This is the visual keras. So here this is the first convolution operation and pooling operation. Everything will be done. After pooling operation, this is the matrix, and then again convolution matrix. Then again this pooling. Then this pooling will be converted into a flatten, and then it is converted, given to an input layer, and then this is the hidden layer, and this is the output layer. So this is the visual keras thing which can visualize the architecture of the neural networks. So everything will be given as, so here the 2 by 2 matrix will be converted to 1 by 1 matrix, one dimensional matrix. Here training here epochs I have given 10, and it is taking times. It will take much times, and it's now in third epoch. Running. Then once we have run the final, once you complete the 10 epoch, the accuracy you can see here, the final accuracy, average accuracy will be displayed here. The final accuracy will be displayed here, taking all these averages. See here the accuracy is almost increasing from one epoch to one training to second training, and the loss is reducing here. If first starting 0.3, then 0.05, 0.03. So the loss is automatically reducing and the accuracy is increasing. This is one type of CNN. So CNN mostly important thing is this part. So how much convolutions and how much pooling you are giving and what activation functions you are going to take. That is the most important thing. So I hope you understood the CNN well. And one more topic we have is RNN. So RNN is up to now whatever elements you have seen in CNN are artificial neural networks, whatever neural networks you have seen, you might have observed one thing that once the information is passed from one layer to another layer, the next layer will not remember anything, will not care about the what happens in the previous layer. But that should not be happen in some cases. So for example, you might have observed when you're writing a mail in Google, once you write a few words, then automatically Gmail will refer you some the next sentence. So if you write I am grateful to, then it will predict the next line. So it will refer some messages like something. So that actually that the reason behind that is RNN network. So RNN, whenever you want to do some sequential operation, otherwise in one more example is translation. So in Google nowadays we are doing more. So yeah, if you are typing something in English, you want to make it in some other language like Telugu. So automatically when you type it in English or if you say it in English, automatically the same in the same sequence, whatever you typed in English or speak in English, the same sequence it will appear in other language. So there we need a sequential thing. So wherever you want a sequential thing, that will go for RNN. So to apply that sequential things, each and every layer should remember what happens in the previous layer. Then only it will remember. Suppose I am going to write a how are you sentence. How are you sentence? I want to ask that mission and I want to predict the mission should say the in the same sequence. So means that the machine should remember the sequence. So first how should come and then R should come and U should come. It cannot say you are how. Then there is no meaning for that. So if you are in translating mode and you are using RNN network, if the sequence is not remembered, then we cannot do anything. Or else in real time Alexa. So if you speak something, if you command something to Alexa, it will give you proper answer. So then Alexa should remember the sequence, whatever you are commanding, whatever you are giving the commands. So in that type of cases, we will use RNN. So uh, anyway, now it's only 10 minutes time is there. So the time is not enough to do hands-on and all these things. So I'll stop here and tomorrow at the starting, I'll start with RNN and then we'll go for GenAI. Now we will share the feedback link and please fill the feedback link. I'll stop the session for today here and we'll meet tomorrow. Thank you. And if you have any doubts, please comment in the comment box. Thank you.